All right, hello physicists. This is our first video of a new semester. We are going to begin with chapter 21 of fundamental physics, and to get ourselves back in the swing of things, we're going to talk a little bit about what we did at the end of last semester. We're not going to talk about class structure. We did that in class, but we are going to revisit some of our ideas about gravity from last semester. Then we're going to introduce electric charge and Coulombs Law. And I want to make a very strong analogy between gravitational forces and electrostatic forces because the laws look almost exactly the same, and the role of mass and the role of charge are equivalent at the beginning here. Okay, so you'll remember last semester I talked to you a little bit about how there is a standard story at this point in physics. And by this point I mean, in the 2020s now, we have our laws that we've tested here on Earth, where we have done very good precision tests on quarks and electrons and all of that jazz. And we didn't talk at all about most of this stuff in Physics 1. When we were talking about effects of these things, we'd use terms like friction or the normal force. So those were electronic forces, but we never talked about the actual form of the electric forces. This semester, we're going to talk a lot about electrons moving around, and we're going to talk a lot about electric fields. And so in the particle picture of the standard model, those are all photon effects. So a lot of this stuff is kind of going to be in the background still. We're not going to, do a lot of stuff with quarks. But lucky thing is, that's most of everyday physics. Most of everyday physics is just electrons moving around, and all of the rest of the stuff is, locked up in the nucleus of the atom. And so, despite the fact that there's a lot of this stuff that we're not going to talk about this semester, by the end of this, you should have a good idea about the fundamental stuff going on the everyday level of normal systems that you're going to interact with in your life. So that's pretty exciting. And then last semester, at the very end, we talked a little bit about gravity. Now, this is the general relativity version of gravity, where you have, the energy, the stress-energy tensor on one side, and the space-time metric on the other side, and a bunch of tensors built out of the space-time metric. And of course, we didn't talk about that, but we did talk about a simplified version of this, a simple version of it where you just think about a gravitational field. Okay, so I want us to go back to that, and of course, I would be remiss if I didn't mention that our cosmologist friends would argue with us about this point, that this covers everything, because they'd say there's also dark energy and dark matter. I will not argue those points in this video. Okay, so let's backtrack. Let's just remember, what did we actually do last semester? Well, we did a lot of things, but just to remember, what are the most important things? Now, I recommended everybody over the summer, if you're going to get a tattoo, you should try to get F equals MA on your knuckles. That's a good one. I had a colleague in Arizona who had just such a tattoo. That's Newton's second law. Newton's first law, of course, was that you need to explain accelerations. You don't need to explain motion. Things, if no forces are acting on a body, we expect it to just keep moving. If we do have forces, we expect it to change the way that it's moving, so we expect it to accelerate. And that's exactly what this said. It says if we add up all of the forces on an object, it will tell us how much that object accelerates if we know its mass. Okay, so we're going to keep that around, and we're also going to keep around Newton's third law. When two bodies interact, the forces on the bodies from each are equal in magnitude, opposite in direction. Okay, so if B is pressing on C, C is pressing on B, those forces are the same. Now, of course, in if you get too simplistic about that, you might think, oh, well, if everything's just pushing on each other, why does anything move differently? Well, it's because objects B and C might have different masses, so they have different accelerations, even if they have the same amount of force. Okay, so the other thing, and this might not be as memorable to you as the Newton's three laws, which I hope are now carved on your heart. The thing that's a little less memorable might be this idea of universal gravitation and the gravitational field. But that's where we need to revisit, because when we talk about electric forces and the electric field, they have almost exactly the same static form as the gravitational. Okay, so what does Newton's law of universal gravitation say? Well, it says that if I have one mass on one side of the room and another mass on the other side of the room, and they're separated by some distance r, and if we wanted to be precise, we would say that their centers of mass are separated by r, then the force on the center of mass of m1 and the force on the center of mass of m2, they're going to be pulled together with the same amount of force, so that's a Newton's third law thing, and the size of that force depends on mass 1 times mass 2, so bigger masses means bigger forces, divided by the distance between the two squared. So the farther away the masses are from one another, the smaller that gravitational force is. Okay? And to make this consistent, we had to put in an extra constant. This is Newton's constant G for gravity. And you'll notice that m squared, this would be in kilograms squared. Remember, our units of mass are in kilograms. And our r squared is in meters squared. And so our g, if g is eventually going to help us to get force on the other side of the equation, here we have newtons, force is in newtons, and we want this whole side to be in newtons. So to get that whole side in newtons, we have to have newtons times meters squared over kilograms squared. So that's the units on g, and then we times it times the m squared. That gives us kilograms squared in the top. So those are going to cancel. And then the r squared, if we put our r in meters, then our meters cancel. And of course, remember, newtons is also built out of those units. So a newton is a kilogram times a meter over second squared. Okay, this is all in SI units. Now, that was our original way of thinking about it. Just, you have a mass, they pull on each other. Why do they pull on each other? It doesn't make a lot of sense that something that's over here would pull on something that's over there. It seems like they should be touching. And so, to get around this, we introduced the idea of a gravitational field. And it's something or other that's surrounding these objects, that's hanging out in space, and the field is the thing that's also over here that's pulling on this object. Okay? And so in this idea, this g, this little g, here on Earth, we know it's around 9.8 newtons per kilogram, because it turns out that the gravitational field strength is the same as the gravitational acceleration. So in this case, the g, if you take it times the mass that you put at that point in the gravitational field, and you take the mass times the field strength, that gives you the force. Okay, so the mass times the field strength gives you the gravitational force. And we're going to copy this next time and say that the force of the electric force is going to be something called the electric charge times the electric field strength. Okay, so that's why I'm going over this. Okay, so here's our Newton's law of universal gravitation, and we did a whole bunch of work with this, for instance, to derive Kepler's law of periods, where when you have an object that's in free fall, if you shoot it fast enough, it will just continue to fall around the Earth. That's what we call an orbit. And we studied centripetal acceleration, such that the centripetal acceleration was equal to the speed of the object squared over the radius of the circle that it's going around. And so we derived Kepler's law of periods, which I'm not going to redo right now. However, your lab this week is going to have you look again at some of these subjects. So one of the things that I want us to do this week is try to think about how we get information out of data. So here is a data set. This is just the radius in astronomical units, and AU is the average distance from the sun to the Earth. So this object here with a 1 AU, that's the Earth. And the time, this is time in Earth years. So the radius of the Earth from the sun to the sun is on average 1 astronomical unit. The time it takes for the Earth to go around the sun is 1 year. Okay, so that's us, the third rock from the sun. And if we go R versus T, these are all of our planets. 1, 2, 3, 4, 5, 6, 7, 8, 9. I guess they have Pluto out on the edge. Now, one half of our lab this week is just working with this and trying to make graphs and being sure that you know how to make a graph with Excel, how to get it into a Word document, so that next week when we write our first actual lab report, you're going to be comfortable with it. So remember, our Kepler's law of orbits says that t squared and r cubed are related to each other. So here's the data for this. If I take this in a graph, at this point, let's say that we just have an XY scatter chart. And I'm just putting this here so you can look at it. This is not a line, and it wouldn't make sense for you to try to plot a line through this. However, if I charted, for instance, my r cubed, so r cubed would have units of astronomical units cubed in this case, versus t squared, so that would be in years squared using these units. Okay, so my r cubed would be, r is at a2 cubed, and then my t squared, this t is at b2. Okay, b2 squared, and I can use my Excel trick and just rip these down, and it will calculate all of those for me. Okay, now if I make a plot of this, let's take a look. Let's make ourselves a scatter chart. That does look nice and linear. And of course, I could make a title for that and say it's my r cubed versus t squared. This is my average radius of my planet going around the sun. T is the period of the planet going around the sun. On my x-axis, I'm going to have my r cubed in astronomical units cubed. In my y-axis, I'm going to have t squared in years squared. And then I finish this, and now because this looks nice and linear, I would want to go ahead and insert a trend line. Let's go ahead, we can force our intercept to 0. We want to show our equation. We want to show our r squared. Okay, so there we go. We've got a graph that we can interpret. And notice right here, now I've been able to get this essentially right out of the data. So if I'm just looking at my data, I had that y equals 1.01 x, but remember my y in this case was actually my t squared, and so that would be 1.01, and my x was my r cubed. Okay, and in fact, because I know the units on this, my t was in years, so this is years squared, and my r was in astronomical units, this would be AU cubed. I actually can tell you what units are on that 1.01 because it has to have, this side also has to overall have units of years squared if these two sides are equal. So there's years squared over astronomical units cubed. Okay, so if I wanted to write out this formula really well, it would be t squared equals 1.01 years squared over astronomical units cubed, and then r cubed. And believe it or not, that is the same as writing t squared equals 4 pi g m r cubed, where g is of course Newton's constant, and this m is the mass of the sun, which we we would say that that's approximately 1.98 times 10 to the 30 kilograms. So this is in very different units. This 1.01 years squared per astronomical units cubed is a weird unit, but we could always change this coefficient into that if we just do a unit conversion. Okay, so a little bit of a long aside, but I encourage you to watch this video to help you get ready to linearize graphs in lab this week. Okay, now just to remember, here on Earth we use G, our gravitational field strength, a lot, and we often just used it as our gravitational acceleration because it turns out that those two things are the same. Why are they the same? Well, because when you drop an object, F equals ma, Newton's second law, can be used as the net force acting on it is just the gravitational force. And when you go ahead and set ma, so that's now our F equals ma net, our acceleration, our net force here is just g, mass of the Earth times the mass of the object times we're drawing, over r squared, the distance between the center of mass of the Earth and the center of mass of our object. Okay, so basically the center of the Earth. These m's cancel out, and there you have your gravitational acceleration, which is just gm over r squared. Now, just to remember, this g, little g, which is big G, Newton's gravitational constant, times the mass of the Earth over r squared. Now, we know what g is in good units. The Earth's radius, if we wanted to put the r in good units, this kilometers is not good units. That's it should be in meters. So this is 6 times 10 to the 3 kilometers. So this would be 6 times 10 to the 6th, 378 times 10 to the 6th meters. Kilograms are good units, meters are good units, and we can just stick this in our equation if we wanted to find that g. So this g would be 6.67 times 10 to the minus 11th Newton meters squared over kilograms squared. And then our mass of the Earth would be 5.972 times 10 to the 24 kilograms. And then our r here, we're going to have an r squared to cancel out this meters squared. This would be 6.3 6.378 times 10 to the 6th meters, and we're going to square that. Okay, so we're sticking in g m over r squared, and since we would actually want to get a number out of that, 6.67 times, I'm going to move this 10 to the minus 11th and 10 to the 24th over because they're hard. They're going to be easier to calculate that way. 5.972 times 10 to the minus 11th times 10 to the 24. Okay, so I have this times this times this times this. I just reordered the way that I'm going to multiply them. And this is 6.378 times 10 to the 6th times 6.378 times 10 to the 6th. So this is going to be 6.378 times 6.378. And then this is going to be divided by 10 to the 6th times 10 to the 6th. I'm doing everything twice because this is squared. Okay, and the units on this are going to be newtons per kilogram, which is also the same as meters per second squared. And what you get, you take 6.67 times 5.972 divided by 6.378 divided by 6.378, and that should give you 0.98. And if you take 10 to the minus 11th times 10 to the 24th, this gives you times 10 to the, this will give you 13, 10 to the 13 over 10 to the 6th times 10 to the 6th is 10 to the 12. Okay, so this is, so that's still in terms of newtons per kilogram. So this would give you 0.98 times 10 to the 13th over 10 to the 12th is just 10 newtons per kilogram. It's just 9.8 newtons per kilogram. Okay, so the reason why I'm going through this is just to remind you about manipulating things with scientific notation, because we're going to use that a bunch this semester when we do our Coulombs Law stuff. All right, so there's our quick and dirty introduction or reminder of our gravity stuff. Now, let's move on. We're going to go ahead and move on to electric charge. So, just like we had every object with a mass in last semester, in this semester we're often going to have every particle having a charge. Okay? And our good units of mass were kilograms, and just like that, we're going to attach a number to an object that tells us something about its dynamics, and that number is going to be called its charge. And the good units of charge are coulombs. This is Mr. Coulomb right here, a distinguished Frenchman, dead, of course. Now, an important thing about electrical charge is that, unlike mass, it can be either positive or negative. Now, why is that so important? Well, the reason that's so important is because most of us we don't carry around a big electrical charge all the time. We do carry around quite a bit of mass all the time because all mass is positive. So you add two masses together, you get the sum of those masses. If you add, on the other hand, here's our little cartoon hydrogen atom. Our hydrogen atom has an electron that's trapped in a cloud around the proton. This electron has the same charge as the proton. So if you add those charges, and you know the E, this fundamental electric charge, is around 1.602 times 10 to the minus 19th coulombs, you might be asking yourself, why such a terrible number? Why didn't we name it 1? Well, I will tell you, there are units called atomic units where that is what you do, but not in this one. We're going to have to struggle with this. The fact that this charge is a very small number, and usually you're going to deal with very small numbers in the charge. And here we have our overall electrical charge of 0, even though, so for instance, I have an overall electric charge of 0, presumably, pretty close at least, despite the fact that I'm made of lots of hydrogen atoms and oxygen atoms and carbon atoms and all that stuff. Okay, so that's why electrical charge is a little different from mass. Other properties of electric charge, it's quantized in the sense that you add or subtract one electron at a time. If you want to get a positive charge, you take off some of those negative charge. You rip off electrons, and that gives you a positive charge because now those nuclear charges, those charges that are tied up in the nucleus, don't have a partner on the outside of some of the atoms. Okay? And if you want to get a negative charge, you grab some electrons, put some extra electrons on you, and you'll have a negative charge. Now, if we have an overall system, electric charge is conserved. So when I rip those electrons off, they don't just disappear. They are sitting around on somewhere else, and then when you touch that object again, it's possible that you'll get a spark, and while you were both temporarily charged, you'll end up with 0. And so there are lots of examples of charge conservation that are more normal, just like rubbing your feet on the carpet and then getting zapped on the doorknob later. That's an example of charge conservation because you pick up some charge, you give it back to the Earth. Okay. There are also more exotic examples of charge conservation. For instance, if you start out with a uranium-238 nucleus, it can split into a thorium and a helium nucleus. These helium nuclei we call alpha particles. So if you have alpha radiation, that's this, and so that's nuclear decay. And you can the mass of this plus the mass of that is slightly less than the mass of the uranium to start out with. So you can use that to get energy out, either in a nuclear bomb or in some sort of a nuclear power plant. There's also something that you won't have to really deal with in this class, but it is interesting that there's things like if you have a gamma ray, that's a very high energy light ray that comes in and barrels into this is a bubble chamber. So this is like a supercooled cloud, and if it bombs into a water molecule, it can cause that basically the gamma ray splits apart into an electron and a positron. So that's an anti-electron, and they go in their opposite direction because they're in the big magnetic field here. So those are sort of interesting, fancy applications that we're not going to worry about right now. Here's an example of the type of homework problem that you will worry about. This is in fact a homework problem on your very first homework assignment. It says, here we have 3 pairs of identical spheres that are to be touched together and then separated. The initial charges on them are indicated. Rate the pairs according to the magnitude of the charge transferred during touching. The charge left on the positive and the charge left on the positively charged sphere greatest first. So let's just consider this one right here. If this has a +6 electron charge on it, that means that it has had 6 electrons taken off of it. This one has a -4 electron charge. That means that it has an extra 4 electrons sitting on it. So this total system, the Q total in that system of just this first ball and the second ball, is going to be 6 minus 4e. So overall the charge is going to be plus 2e. 6 minus 4 is plus 2. Okay, so at the end of the story here, if these are going to share their charge between them equally, they're each going to end up with half of that. So it's just going to be plus e plus 1e. Okay, so what happened here is that this electron, when these two touch, it gained 5 electrons. So it went down. It became more negatively charged. This one, on the other hand, got a charge that is 5e more, so it lost 5 electrons. Okay, so it gave up all its extra electrons to this, and in fact, it gave up an extra electron too. Okay, so I want you to think through the other ones, but being able to tell stories like that is a big part of what I want you to practice today and practice in our lab this week. Now, what we're going to really practice in lab is trying to understand how is it that you can charge objects. Okay, if everything is just made of a whole bunch of different charges, how is it that you're able to get them to be charged? Well, this is a picture of the triboelectric series, and you can categorize different objects that are insulators. So this is my coffee mug. It's made of metal. Metal is a conductor. Electrons move around very easily within conductors. They don't move around so easily within insulators. Insulators are things as diverse as fur, glass, nylon, wool. They're things that you usually wouldn't think about making a wire out of. You wouldn't make an electric wire out of any of those things. But if you rub them together, some of these objects like to lose electrons. So they'll end up with a positive charge after rubbing. Some of them like to gain electrons, so they'll end up with a negative charge after rubbing. So one way to get a charge on an object is to take one of these objects with a negative affinity, like let's say a rubber balloon, and an object with a positive affinity, let's say something like silk. And if you rub silk on a rubber balloon, okay, there's my silk, there's my balloon. What you will find is that the balloon ends up with a negative charge and the silk ends up with a positive charge. Okay? And of course, what this means is that if you take two of these, the opposite charges attract. So these are going to stick together. And if you have two of those balloons that are charged, they're going to repel. So opposites attract, likes repel. We will come back to that in a second. Now, if you have something that's a conductor, you can also charge it, but you're not going to be charging it by rubbing because the charges can just move around very freely. So you usually would take an insulator, get it charged up, touch it to a conductor, and then if the conductor is connected to an insulator, for instance, like the top of my coffee mug, then it will just hold this charge. Now, how do I go ahead and get it to charge with another conductor? Well, one way is just by touching them together. Okay, so if I touch these together, some of that charge will leak off onto this other one, and now they would both be charged. Now, it's not so easy to keep something charged. Sorry. So often, if I, for instance, had this charged and I just touch it, the electrons would leak off into my hand and go into the ground, and we would call that grounding the object because the electrons are going back into the ground, the literal earth ground, and then it would lose its charge. Another way to charge an object that's a conductor is a little bit harder to understand, but here's a nice picture of it. Suppose that you had an object that's negatively charged. Okay, so this one starts out with a charge on it, and then I bring a second object that's a conductor close to it. Now, because electrons can move around freely in this, the positive charges on this are just from the electrons having run away. So the electrons here, like charges repel, are going to push the electrons in this object away. So they are all going to gather in the other side. We call this a polarization effect. So this object is polarized because the charges are separated within it. One side of it is more positively charged, one is more negatively charged. Then if you go ahead and touch that object, those electrons are able to flow off onto your finger into the ground. Now I have two objects that are charged. This one has a positive charge and that one has a negative charge. And of course I could uncharge them simply by touching them. Okay, so we are going to look at that in a lot more detail in lab. You're actually going to do this. But before you get to lab, I would recommend watching this video because I don't think that I have described it very fully. Paul Anderson here of Bozeman Science gives a nice explanation, so I recommend you watch that before you come to lab, and that's going to help you out a lot. Okay, so last thing today, and the most important, and one of the most important ideas of this first unit. We are going to write down a rule that looks exactly like Newton's law of gravity, except for charges. Now, the difference, of course, is that the electric forces, it depends on a number out front, the charge on the first object, the charge on the second object, and the distance between them. Okay, so if you want to find out how much force is acting to push these two particles away or to pull these two particles together, you would take this constant number times Q1 times Q2 divided by the distance squared. And just like with our gravity, the units here for this thing, this is in newtons, this is in coulombs. Remember, the units on charge are coulombs. Those could be positive or negative, but we're going to take the absolute value, and the thing that tells us whether this is pulling together or pushing apart is that like charges repel, like charges push each other apart, opposite charges attract, they pull each other together. Now, what units does this number have? Now, I'm claiming this is actually going to be a very big number. This is going to be coulombs times coulombs over r squared, so that's meters times meters. And so the units on this whole thing have to be newtons, because both sides have to have overall units of newtons if it's going to equal the force. And then I need to have meters squared over, and I need to cancel out these coulombs over coulombs squared. Okay, so these newtons cancel out, coulombs cancel out, and I get to newtons. So this k out front, which is 1 over 4 pi epsilon naught, that's a little bit of a weird historical artifact. The epsilon naught is called the permittivity of free space. We'll talk more about that later. But for now, let's just think about this as a number. It's a big number. It's around 9 times 10 to the 9th Newton meters squared over Coulomb squared. And if you stick this in, stick in the two charges, and stick in the distance, you will get how much force you have. And I really want to stress that this looks almost exactly like Newton's law of gravitation. Look, you've got a constant out front, charge over r squared. With Newton's law of gravitation, you had constant out front, mass over r squared. So in this case, the mass and the charge basically have the same role, and then there's a distance, that's all the same, and then there's a constant. Now notice what's different is that these can be either plus or minus, so Coulombs law can push objects apart if you have a minus and a minus or a plus and a plus, or it can pull objects together. And then the other difference is sort of in the scale. Notice this k is a very big number. G was a very small number, 10 to the 9th, 10 to the minus 11th. Of course, that's sort of, it is true that gravitational forces are much weaker than electronic forces, but I will say it's a little bit of a figment of the units that we've chosen as well. Okay, so to do problems with this, we need to be prepared to use our train tracks. Remember, the example that I gave last semester at the very beginning was, what if you were filling a field with water at a rate of 5,000 feet cubed per minute, and you wanted to change that to units in terms of meters cubed per second. Well, you could do that because you know how many meters are in 1 foot, and if you wanted to change feet cubed to meters cubed, you'd have to take that term times itself 3 times, so 0.3048 times 3.3048 times 0.3048, and that gives you a small number right there, and then minutes per second. So then you have your feet cubed, cancel out with the feet times feet there, and then you would have your minute cancel out with the minute right there, and that would give you something in terms of meters cubed over seconds. So that was the example that I gave you last semester. We're going to have to make sure we always do that this semester as well, because we're going to have questions like this. So this is very similar to a question that's on your homework. Let's say you have 2 tiny spherical water drops with identical charges of this. So that's a small amount of charge. It's made of several electrons. They have a center-to-center separation of that. Notice this is in centimeters. 1 centimeter is bad units. You're going to want to get that in terms of meters before we stick it into Coulombs Law. The first question is, what is the magnitude of the electrostatic force acting between them? So that's where we're going to use Coulombs Law. And then how many excess electrons are on each drop, giving it its charge imbalance? So for that, you're going to use the elementary charge. This is the amount of charge that's on each electron. And I believe, let's try it here. Okay, so what is the magnitude of the electrostatic force? So we have Q1 and Q2 are the same. They're both -1 times 10 to the minus 16th coulombs. Coulombs are good units here because the K that I have is in terms of coulombs. You could be given something in terms of microcoulombs or nanocoulombs or something like that. So you would have to be sure to get your units in the correct terms. With the center-to-center separation, so that's between this and this, of 1 centimeter. So that we're going to want to get into correct units. So 1 centimeter, and just to use my train tracks here, I would have 100 centimeters is 1 meter. Okay, so this is 0.01 meters, or if I want to put that in scientific notation, 10 to the minus 2 meters. Okay, so now if I want to find the force, I would go ahead and I would put that in as K. That's this number out front, so that would be 8.99 times 10 to the 9th Newton meters squared over Coulombs squared. Q1 times Q2, so that's going to be the absolute value here, 1 times 10 to the minus 16th coulombs, so that's my Q1. 1 times 10 to the minus 16th coulombs, that's Q2, over R squared. So that's going to be 10 to the minus 2 meters squared. Okay, let's go ahead and rearrange that a little bit. 8.99 times, so here my Coulomb squared cancels out with coulombs and coulombs. My meters squared cancels out with meters squared. And so I'm going to have right here 10 to the 9th, 10 to the minus 16th, 10 to the minus 16th over 10 to the minus 2, 10 to the minus 2. And that's going to eventually give us a force that's in newtons. That's good. Okay, so the force here would be 8.99 times 10 to the, okay, so this is 10 to the minus 32 plus 9 would give us 10 to the, let's see, minus 23, I think. And then this would give us 10 to the minus 4. Okay, so that should give us 8.99 times 10 to the minus 19th newtons. Okay, so very small force, but they're very small drops. And then it asks how many excess electrons are on each drop. So I could go ahead and say I have a N equals the total charge divided by the charge per electron. Okay, and that would be a minus E because that's the charge on the electron. So it would be minus 1.00 times 10 to the minus 16th over 1.602 times 10 to the minus 19th, and these are both in coulombs. This should just give us a number. And I put this in my calculator earlier, and I believe it's right around 625 electrons. Should be a minus there. Okay, so that is the way that you do that sort of problem. All right, so that's enough for today. What have we learned? Well, we went over our gravity stuff, so we want to keep around some of our Newton's laws ideas, but our new ideas in this video are that we can have insulators that have different electrical affinities, and so if you rub them together, you can predict which one's going to end up with a positive and which one's going to end up with a negative charge. We talked a little bit about how conductors can be charged by either conduction, that's just touching them together, or induction, that's where you have one charged object, another object without a charge that you bring close to it, and then you touch it and let some of the charge leave or come onto it that way. So we're going to investigate that more in lab this week. We talked about how electrical charge is quantized. That means that the amount of charge goes on or comes off one electron at a time, and it is conserved, so that means that the total amount of charge in any closed system is going to be the same before and after you rub your hands together, for instance. And then we learned how to use Coulombs Law, which looks just like Newton's law of gravitation, and it relates the electrical forces to the magnitude and the displacement of electrical charges. Okay, so thank you for watching. We'll be back in a couple days.